So that's actually a really good question because I didn't start out as a chemist. I actually started out as a biologist. So in undergrad, at the time, I wanted to be a geneticist. So I was a biology major. And as I continued taking classes in undergrad, I realized that I had more of a passion and curiosity about the inner processes of the cell. So how does the cell function the way that it does? What triggers it? What stops it from doing a certain process? And I found that really engaging and interesting. So I continued studying more and more about that until eventually I arrived at the atomic level. So what are the molecule signals? And why do molecules behave the way they do? And eventually I found that my chemistry courses were sort of feeding that curiosity a little better. And I ended up adding my chemistry major as a junior in undergrad. We play a lot of different roles in our position. So not only do we have our teaching role in which we're developing courses, developing activities and lesson plans and assessments and continually researching and adapting our pedagogy to adapt to our changing students' needs. We're also still actively engaged in research. So I'm writing grants and writing papers and collaborating on projects and training and mentoring students in their own projects. I'm also an advisor, so I advise students all across the curriculum in order to make sure that they graduate on time and also that they meet all of their major requirements and get the courses that they need. And also be there as an ear for them when they're running into challenges. Additionally, we play administrative roles for the college. So often, we are asked to serve on committees. I've served on the assessment committee and the IRB committee, do a lot of planning committees and search committees. I also serve as our local section secretary for the American Chemical Society. So I'm constantly networking with chemists across central Alabama in order to help design events to help foster an enthusiasm for chemistry in our community and engage a younger generation of chemists within the ACS as well. Being able to communicate effectively and adapt that communication for your audience. So knowing what your audience is and adapting what is the information you're trying to get across tailored toward that audience and their needs. If I'm delivering information to my undergraduate students in my biochemistry course, I would deliver that very differently than if I was delivering that information to colleagues at a professional conference who have a very precise skill set. So one of the best experiences that I had that helped foster the skill of communication was all through undergrad. I had to work full time. I had to pay my way through college. And I worked as a bartender and a server at a small restaurant. And my customers got to know me really well. And they would often ask me about my research, what it is I wanted to do, and my studies in undergrad. So it gave me a lot of opportunities to network, as well as a lot of opportunities to sort of share my joy and enthusiasm for chemistry and talk a little bit about my research to a wide range of people. In this video, we're going to be focusing on determining how many significant figures you have in a value, as well as how to calculate using significant figures. So when I talk to students about significant figures, the most common questions I get are, what are significant figures and why do we care? Well, in order to understand why it is that we as scientists care about significant figures, we first must differentiate between exact values and measured values. So take this apple, for instance. This is one apple. It's exactly one apple. It's not 0.99 apples. It's not 1.002 apples. It is 1.00000 with an infinite number of significant figures apple. This is an exact value. Now, if I were to cut this apple in half, in order to determine how well or how precisely I cut this apple in exactly 1/2, I would have to do a measurement. One way that I can measure how good I was at cutting the apple in half would be to weigh the apple whole, cut it in half, and then weigh one of the halves. So one tool that I could use to weigh the apple might be your typical bathroom scale. So this is a scale that you might have in your own dorm that can weigh pounds up to 1/10 of a pound typically. So if I weighed my whole apple on the bathroom scale, let's see, so the whole apple, it might weigh somewhere around 0.3 pounds. When I cut the apple in half and weigh one of the halves, it might weigh 0.1 pounds. If I compare 0.1 pounds to 0.3 pound in order to determine the percent of the apple that the 1/2 is, I end up with about 33.33%. Doesn't seem I was very good at cutting that apple in half in terms of the bathroom scale values, is it? The bathroom gives us 1 sig fig with the 0.3, 0.1. Now, if I use an analytical balance that you might have in your Gen Chem lab, these can typically weigh grams up to the 100th of a gram. So when I weigh the whole apple, I might end up with a weight of 103.25 grams, giving me 5 significant figures. When I cut the apple in half and weigh one of the halves, I end up with 53.24 grams. Again, now I have 4 sig figs. When I compare 53.24 to 103.25, in order to get a percentage, I calculate that I have 50.69% of the apple. That's much closer to 1/2 of the apple as determined by the analytical balance than was the bathroom. The difference here is that I had much more confidence or more significant figures in my values using the analytical balance compared to the bathroom scale. So to determine the number of significant figures a measured value has, you only need to follow these rules. First, all non-zero digits are significant. For instance, the value 1.234 grams has 1, 2, 3, 4 significant figures. Additionally, the value 1, 2, 3, 5 centimeters also has 4 significant figures. Rule number 2, all zeros between digits are significant. For instance, 102.3 grams has 4 significant figures, or 1.0056 milliliters has 1, 2, 3, 4, 5 significant figures. Another rule, all zeros before a non-zero digit are not significant. So for instance, 0.0006 milliliters has 1 significant figure, or the value 0.0123 centimeters has 1, 2, 3 significant figures. Again, these non-zeros and these zeros are not significant. Now our last rule, all zeros after a non-zero digit are significant. So for instance, 1,000 liters has 1, 2, 3, 4 significant figures. And 1.002 centimeters also has 4 significant figures. Okay, so now that you know these rules, let's practice. So in the following questions, I want you to tell me how many significant figures are in the given measured value. So now that we know how to determine the number of significant figures a given measured value has, how do we calculate with significant figures and determine how many significant figures our answer should have? Again, we have some simple rules that we can follow in order to help us determine this. 1, when adding or subtracting with measured values, the answer should have the same decimal place as the smallest decimal place value. So for instance, if we had 1.000 grams plus 0.2 grams plus 0.045 or 54 grams, right? The whole answer would be 1.254 grams. However, the 0.2 grams has the smallest decimal place. So we need to round our value to 1.2 grams, or if you round up, it would be 1.3 grams. Either way, we end up with 2 significant figures. When we are multiplying or dividing with measured values, then we use the value with the smallest number of sig figs. So in this case, we go by the sig figs, not the decimal place. So if we multiply 1.002 centimeters times 0.0005 centimeters, we end up with a value that's 0.0000503 centimeters squared. Now, 1.002 centimeters has 1, 2, 3, 4 sig figs. This value only has 1 sig fig. So our answer, therefore, must be rounded to 1 sig fig, or 0.0005 centimeters squared. So now let's practice a little bit. I'll give you some questions that ask you to either add, divide, subtract, or multiply various measured values. And based on these rules and the rules in determining the number of significant figures, calculate the answer to the correct number of significant figures. So now that you have a better understanding of how to determine the number of significant figures a given measured value has, as well as how to calculate using significant figures, why don't you rewind and go back to my apple example and see if you can catch the mistake that I made earlier. Okay? Well, I hope you have a very significant day.